just picking up with where we have left off, and we were looking into functions once again and polynomials, and we crossed over to the topic of zeros and their multiplicities, and we're going to resume with that and just look a bit further into the makeup of all that stuff, and just looking at what we have, like in the case of forming polynomials from zeros and their given multiplicities. And we'll take as a case here if we're looking at determining f of x. In both factored and expanded form. And we'll say we have given, say for the first case, we'll say we have for the zeros. Okay, we'll say we have 0 and have 0 to consist of a multiplicity value of 2. And also in the mix, okay, we'll say we have another 0 at 5. And we'll have this multiplicity to also be at 2. And we'll say that for the degree of the expression. We'll have this as a fourth order polynomial. Okay, so we have in the case of what we have for the zero values of 0 and 5. Okay, we can say that 0 can stem from x equal to 0. And now, okay, so the factor of concern, okay, we can say is going to be x or any direct multiple of this. And okay, so from 0 we have an x factor, and with 0, okay, 0 has a multiplicity of 2, and by definition, okay, the multiplicity of a 0 is going to be the degree to which the factor corresponding to that particular 0 is going to be raised. Okay, so with the multiplicity of 2, okay, we have not just x, but x to the second. And in the case of what we have with the value of 5, we say this originates from setting equal to 0 the binomial x minus 5. And we have for the factor corresponding to that 0, okay, we have x minus 5. And since 5 has a multiplicity of 2, okay, just like x moments ago, we have the factor x minus 5 to also be raised to the second power. So for the factored form, you'll see our polynomial is going to be f of x. Okay, so you have x squared. We have times the square of the binomial x minus 5. So this is a factored form of what we have for this polynomial with the given zeros and corresponding multiplicities. Now, if I'm looking at an expanded form, say if I have this to be the factored form, okay, so you have f of x is equal to x squared. And for the square of x minus 5, we can just rewrite this in terms of multiplying. So you have x minus 5 times itself. And you could go ahead and square the binomial and just multiply that all by x squared. Or if you were to just do it a bit incrementally. Say if I were to multiply x squared and the first x minus 5 that appears. So we have for this product, okay, we're going to have x squared over x is going to be x cubed. We have x squared over negative 5 is going to be negative 5x squared. And we have weighting to be multiplied. Okay, so you have the other x minus 5. And in the case of FOILing out, okay, so the first product you have x cubed times x. So this would be x to the fourth. Outside product, okay, we have minus 5x cubed. Inside product is another negative 5x cubed. And the last product, have a negative times a negative is a positive. In this case, we have 25x squared. And we have now for the expanded form, we have f of x is equal to, we have x to the fourth. Combining the middle two terms, we have negative 10x cubed followed by once again the addition of 25x squared. Alright, another situation, okay, so this is like taking the zeros and their multiplicities, forming a polynomial in both factored and expanded form. Okay, so this is a case. Right now, if I were to work in reverse, say I had a polynomial in expanded form, and I wanted to find out what the corresponding zeros and their multiplicities would be. Now let's say that if I were to determine say the zeros and their multiplicities, and we'll say we have, in this case, right, so we have f of x is equal to, let's say we have x to the 8th plus 12x to the 7th minus 28 times x to the 6th. Okay, so we have for this particular polynomial function, okay, so we got this high degree expression. And all of these terms will consist of the variable x, okay, and if you notice, okay, the greatest common factor, okay, now for the coefficients, you have 1, 12, negative 28, highest number divisible into those coefficients is only 1. Now the greatest common factor is going to be in the letter x, and highest term that will go into all three of these is going to be x to the 6th. And if I factor out x to the 6th, okay, so we have x to the 6th times all of x squared plus 12x, and x to the 6th into negative 28, x to the 6th, that's just going to be minus 28. And if I look at factoring further, okay, so you have x to the 6th already squared away. And for x squared, so this will factor out to x and x. And factors negative 28 with a sum or difference on the plus side at 12. Okay, we're going to have more weight given to the addition than to the subtraction. So in this case, we're going to have x plus 14 and x minus 2. Okay, so this is going to be the factored form. And just rewriting this and emphasizing the degree of each factor. Alright, so we have, first factor we have x, okay, and that is to the 6th. And for x plus 14, okay, you don't see a raised exponent, okay, so that is implicitly x plus 14 to the 1st. Likewise for x minus 2, just that binomial, we have implicitly that this factor is raised to the 1st. So we have, in the case of the zeros and the multiplicities, okay, so we have first factor again is x, and again, I've already set x equal to 0, well we already have 0, and since x is to the 6th order, we had that multiplicity to be at 6. For x plus 14, if x plus 14 is equal to 0, we have that x is equal to negative 14. And since the corresponding factor is raised to the 1st, that multiplicity is at 1. And for x minus 2, we have x equal to 2. And since the corresponding factor is not raised to any higher power than 1, okay, we have 2, like negative 14, is going to have a multiplicity value of 1. So this is a case of what we have determining the zeros and multiplicities from a given polynomial that is presented in expanded form. Now, for what we have from the group of problems from page 266, and we're looking at the attainment of zeros and multiplicities. And for what we have in the case of the first items, okay, we have the layout in terms of expanded form. So we got f of x is equal to x cubed plus 2x squared minus 25x minus 50. Okay, now, we're not splitting up a single term into two terms in the same degree in x, okay, but with the way that this particular polynomial is laid out, I'm still able to utilize factoring by grouping. One reason is that, okay, we got the terms in descending degree order, and another primary reason, let me put it this way, descending degree order going down 1 degree in x at a time, from 3rd order, 2nd order to 1st order to a constant. And the second key factor is that for the second term relative to the first, if you take the coefficients, you got 2 from 2x squared, and you got 1 in reference to x cubed, and so you had the second to first coefficient is going to be like a 2-to-1 ratio. And the last two terms, you got like negative 50 to negative 25. Negative 50 to negative 25 is also a 2-to-1 ratio. And with the way that the degrees are situated, and in terms of how the coefficients are lined up, I'm able to perform factoring by grouping. Most polynomials will not be able to do this, but for this particular case, all right, we do have things lined up where this is possible. And so for x cubed plus 2x squared, I can group this together. And we have for the middle operation, okay, we got the subtraction, separating the 2x squared from the 25x, so we got subtraction in the middle. And if I were to envision factoring out negative 1, you got minus 25x, so it would be the opposite sign of 25x. And negative 50 is going to be the opposite sign of plus 50. So you have two pairs here, and I can draw out the greatest common factor. And for the first two terms, we're going to have x cubed plus 2x squared. Greatest common factor, okay, we have in the variable x, and that is going to be x squared. And taking that into x cubed plus 2x squared. So we have the quantity of x plus 2. we have with subtraction. Now for 25x plus 50, okay, so just kind of sidestepping away from the prior terms in operation, greatest common factor between 25x and 50, that is going to be 25. And taking 25 into 25x plus 50, that's going to be another formation of the binomial x plus 2. Now looking at what we have in the follow through. Okay, so you have a common binomial with x plus 2. And with the outside terms in operation, we have x squared minus 25. So you have a difference of squares. And we can follow through and factor even further. So you have f of x is equal to, once again, x plus 2. For x squared minus 25, okay, we have an x plus 5 and an x minus 5. Again, the order of these factors does not matter. And again, just stressing the powers. Okay, so this is our factored form. Okay. And again, not an absolute must, but I'm just going to, again, stress the degrees. So you got 3 distinct factors for which we're going to have 3 distinct zeros. Okay, so for x plus 2, if x plus 2 is 0, we have x equal to negative 2. And since the corresponding factor is a first order, well, negative 2 has a multiplicity value of 1. For x plus 5, we have negative 5, and the multiplicity of that is also at 1. And for x minus 5, okay, so we have positive 5, and since the corresponding factor is a first order, we have the multiplicity to also land at 1. So in this outcome, we have 3 distinct zeros, but each one of these will all have a multiplicity value of 1. All right. Now, for what we have in the case of, let's see, for number 28, okay, we're going from f of x to n of x. Again, just another way of saying y. In this case, we have like the equivalent of y is equal to x to the 6th plus 4 times x to the 5th plus 4 times x to the 4th. Okay, and for this item, okay, we have the greatest common factor we can draw out. Okay, so that's going to be 1 times, okay, or just x, and this will be to the 4th. And factoring out x to the 4th, so I got x to the 4th times, and x to the 4th into x to the 6th is going to be x squared. X to the 4th into 4 times x to the 5th is going to be 4x. And we have x to the 4th into 4x to the 4th will go 4 times. And we can continue factoring. So you have x to the 4th. X squared plus 4x plus 4. This would be a case of where we have a squared trinomial, meaning that you're going to have the same binomial factored out and just clustering together. Okay, so we got x to the 4th. Now for x plus 2 times itself, okay, I want for there to be one appearance explicitly for any factor that repeats. Okay, so we have x plus 2, but to signify that x plus 2 repeats once, okay, we have 2 of these to show up. So we have n of x is equal to x to the 4th, and then we have times the square of x plus 2. And Again, just looking at the zeros and the corresponding multiplicities. All right. So you're going to have x raised to the fourth. And have x plus 2 raised to the second. So we have two distinct variable factors in x. So from just x, we'll have 0, and because x is raised to the fourth, we have that the multiplicity is at 4, and from x plus 2, we have x equal to -2, and the corresponding multiplicity value is going to be at 2. Now, so again, both 23 and 28 are presented in the expanded form. Now, if I look at where we have a factored form already provided, and when the polynomial is given in factored form, chances are you'll be able to get to the zeros and their multiplicities more quickly. Okay, and in 29, okay, so we got the function p of x. Again, another way of saying y. And we have is equal to -3x. We have times x plus 2 raised to the third. Then we have times x plus 4. Okay, so this is the factored form, and if I rewrite this, just stressing the degrees, and in effect the multiplicities. Okay, so I'm going to have for -3x, that's like -3 times x to the first, and already have the cube of x plus 2, and for x plus 4, again, no explicit power given, so we just read this as if it were the first degree of x plus 4. And for the zeros, okay, now the -3 is just a coefficient, but I'm interested in just the variable factors. Okay, so with -3x, variable factor is x, and if I were to set like -3x equal to 0, I would have x equal to 0, and the variable factor is just a first order. So the multiplicity equal to 1, and then we have next from x plus 2. If I set x plus 2 equal to 0, I have x equal to -2, and since the corresponding variable factor is raised to the third, -2 is going to be a 0 that has a multiplicity of 3. And for x plus 4, if I set this equal to 0, we have x equal to -4. And just like 0, okay, the corresponding factor is only a first degree. So -4 is going to have a multiplicity value of 1. Okay, so those would be the zeros and their corresponding multiplicities. Now, for what we have in the case of number 30, okay, now we got q of x. Okay, and that is set equal to -2, x to the fourth. We have times the cube of x plus 1, and then we have times the quantity of x minus 2 to the second. Okay, so I have a factored form, and just looking at what we have here. Okay, I'm just stressing once again the degrees. Okay, so from the first factor, again, -2 is just a coefficient, And for the variable factor, we have x, of which we have 0. And since x is fourth order, we have the multiplicity to be at 4. And with x plus 1, okay, we have -1. And since we have the cube of x plus 1, the multiplicity value of that 0 will be at 3. And for x minus 2, so we have x equal to 2. And since we have the square of x minus 2, we're going to have the multiplicity at 2. Alright, so we're still looking at the mechanics of the whole thing, but it is going to become a part of how the graph of a function is going to behave, which we're going to be looking into shortly. Now, so far we've had all the zeros to consist of integers. Okay, we have zeros as well as positive and negative integer values. But you also have zeros to be consisting of non-integer amounts. And now number 38 is going to be such a case where we have y is going to be represented by m of x, which we have given as a fifth order function, where we have x to the fifth minus 5x cubed. All right. So we have here, okay, for this difference of terms, okay, now again we have a greatest common factor in the letter x. So here we'll have m of x is equal to, and greatest common factor is x cubed, and into x to the fifth minus 5x cubed. So we have x squared minus 5, and I can continue, but I will have some irrational roots in the mix. So that m of x is equal to x cubed. Now for x squared minus 5, think along these lines. Okay, so you have like x squared minus p. Not the square root property of equality, but where you can factor it. You have for a difference of squares, like x squared minus p is going to be x plus the square root of p times x minus the square root of p. And for, think of like p being represented by 5, and again 5 is not a perfect square in the integers, but in exact terms I can say that like x plus the square root of p is going to be x plus the square root of 5, and for x minus the square root of p we'll have x minus the square root of 5. Okay, so this will be the factored form. Again, just emphasizing the degrees. Okay, so you have x to the third. And for x plus as well as x minus the square root of 5. Okay, so that'll be to the first. Okay, so for what we have in the case of the zeros, okay, so you got your x standalone x factor, of which we're going to have 0, and since we have the factor at x to be cubed, well, the multiplicity of 0 is going to be 3. And for the others, now we're going to have irrational roots. Okay, now for x plus the square root of 5, if I were to set that equal to 0, I would have that x is equal to the negative of the square root of 5. And since that factor is a first degree, we say we have minus the square root of 5. Okay, so the multiplicity is going to be a 1. And for x minus the square root of 5, okay, If I set that equal to 0, well, we have the x is equal to the square root of 5. And since that corresponding factor is a first degree, okay, we have, just like the negative of the square root of 5, we have the positive to also end up being a 0. That will have a multiplicity value of 1. All right, and so again, we're going to be soon looking into the behavior of the graph of a function, and tell you what, just for the next few minutes, okay, let's see what we get for the zeros and the multiplicities. Let's say we have with the first function, and we say we have f of x is equal to 2x to the 4th plus 4x cubed plus 2x squared. And we'll say we have with the second one, we'll say that we have f of x is equal to x to the 6th plus 10 times x to the 5th, and we'll say we have plus 25 times x to the 4th. So let's see what we get with from these polynomials, what the zeros and their corresponding multiplicities will be, and we'll discuss in the next few minutes. Okay, all right, here we go. Had a technical issue to take care of. Okay, so looking into what we have with these polynomials. Okay, so we have, first of all, we have f of x is equal to 2x to the 4th plus 4x cubed, followed by 2x squared. And if we look at factoring, okay, so we have for this f of x, okay, so you have the greatest common factor in the mix. Okay, if you notice, we have all the coefficients are even. So we got 2x to the 4th, 4x cubed, 2x squared. So the greatest common factor we're going to have with 2x squared. Okay, so 2x squared is going to be the greatest common factor. And factoring out 2x squared, okay, so we'll have x squared and 2x squared into 4x cubed, okay, that's going to be plus 2x. And 2x squared into itself is going to be 1. Here we have the presence of a square trinomial. So we have the f of x is equal to 2x squared. Times x plus 1 times x plus 1. And again, rewriting. Okay, so I have a factored form, but I want to do it without the same expression written more than once, or on display more than once. Okay, so I have 2x squared, and with x plus 1 times itself, anytime you have a repeating factor, you take that factor and raise to the number of times that it shows up. In this case, we have to the second, so you have 2x squared times the square of x plus 1. So we have, in the case of the zeros, okay, so we got with the variable factors, we have 2x squared and the square of x plus 1. Again, just stressing, okay, so we got x is to the second, and we have x plus 1 likewise is raised to the second. And from the variable factors of x and x plus 1, we have the corresponding zeros, where we have 0 with a multiplicity value of 2. And from x plus 1, we have -1, which we have also with a multiplicity value of 2. Now, for what we have with the sixth order polynomial, okay, for this f of x, okay, so you have x to the sixth plus 10 times x to the fifth plus 25 times x to the fourth. And for this set, now x to the fourth is going to be the greatest common factor. And taking x to the fourth into this expression, so we have x squared plus 10x plus 25. Okay, so we have x to the fourth, and with x squared plus 10x plus 25, okay, this is going to factor out to x plus 5 times itself. Okay, so you have, again, you have x to the fourth, and just like x plus 1 earlier, okay, you have x plus 5 to repeat. Okay, and again, just emphasizing the degrees of the variable factors. Okay, so x is to the fourth, and we have x plus 5, okay, so that is going to be to the second. So you're going to have with the zeros. Okay, so from x we have 0. And we have the multiplicity at 4. And from x plus 5, okay, we have x equal to -5. And that multiplicity is equal to 2. All right, and in terms of the dynamics created, okay, for what we have for the graphs of polynomial functions, okay, now zeros and multiplicities will have their own individual purposes, and for what we have in the case of zeros and multiplicities, okay, now looking at what we have in graphing. Okay, whenever f of x gets to the x-axis and interacts with whatever is on the x-axis, okay, there's some procedures here in terms of how f of x is going to follow through. Okay, first of all, in graphing, f of x is going to cross the x-axis. At zeros of odd multiplicity, okay, so just stressing the words here, so it's going to cross the x-axis whenever we had the zeros to be of odd multiplicity, but in other cases where there are zeros, okay, f of x is going to touch the x-axis. At zeros of even multiplicity. So if you had the buzzwords here, so you had to touch the x-axis whenever you had the zeros to be of even valued multiplicity. Okay, and they'll give you just case here in terms of the behavior of the graph of a function. And let's say we have, and I'll just lay this out in factored form. And let's say we have f of x is equal to, and let's say we have x plus 2 raised to the 4th times the quantity of x minus 3. So we have this to be to the 2nd. Now we'll say we have times the quantity of x minus 6, which would be raised to the 2nd. And we have times the quantity of x minus 10, which is raised to the 3rd. Okay. And going back to the activity, so you're looking at crossing at zeros that will have the factors to be a power that is an odd value, whereas you're going to have the graph to touch the x-axis at zeros, where the corresponding factors are raised to an even power. And it is possible for odd numbers to have even multiplicity and vice versa. And this is going to be a case where we're going to have a bit of a mixed bag. We might have even values or even valued zeros with an odd multiplicity as well as an even multiplicity. And now for this particular polynomial, okay, if I were to identify the zeros, okay, so we have an x plus 2. If I set that to 0, we have negative 2. If x minus 3 is 0, and so let me stress this. So I have x equal to negative 2. If x minus 3 is 0, we have x equal to 3. And if x minus 6 is 0, we have x equal to 6. And if x minus 10 is 0, we have that x is equal to 10. Now for the multiplicity, okay, so negative 2 stems from x plus 2, which is to the 4th. So the multiplicity is going to be at 4. For the value of 3, okay, we have this to stem from x minus 3 to the 2nd. So have a multiplicity of 2. And likewise for x minus 6, okay, we have the 0 at 6, but again, with the square, 6 is going to have a multiplicity value of 2. And for x equal to 10, okay, now we have an even valued 0, but since the factor is raised to the 3rd, this is a case of where you have an even valued 0 that is going to have an odd valued multiplicity. And we have at those zeros, okay, in terms of whether it's going to cross or touch the x-axis. Okay, so we have here, I'm going to use like T for touch, C for cross. And okay, so you have multiplicity value is 4. And again, so 4 is an even value, and it's going to touch the x-axis. So in this case, it's going to touch, and where is it going to touch? Well, it's going to touch at x is equal to negative 2. And for x equal to 3, 3 has an even multiplicity. And for the same reason, at that 0, it is going to touch. And for x equal to 6, okay, you have an even multiplicity, so at that location, it is going to touch. And out of the 4 zeros, only 10 has an odd valued multiplicity, and so it is there that you're going to have the graph to cross at x equal to 10. So in the sort of the makeup of things, okay, so this is what we got. We got 4 distinct zeros, 3 with an even multiplicity, 1 with an odd valued multiplicity. and just looking at the behavior of the graph of this function. And we'll throw in some more details in a moment. Okay, but you got your zeros. Okay, so you have -2, along with +3, +6, and +10. Okay, and just looking at how the graph is going to appear. Okay, so let me just kind of stress. Okay, so at -2, okay, the graph is going to touch. At 3, it is also going to touch. At 6, it is going to touch, but once we get to x equal to 10, okay, so the graph is going to cross. Okay. All right, so we got, in this case, right, so we have for the graph itself, okay, so you have to touch at these zeros and cross at the other. And so for the graph of what we have for f of x, I'll go with this color. Okay, so we'll start out, say, beneath the x-axis. So once we get x equal to -2, instead of crossing from below to above, it's just going to touch, kind of bounce off the x-axis. It's going to dip and then it's going to rise. And once we get x equal to 3, have a bit of history to repeat. So it's going to touch against, and again just bounce off. And once we get to 6, okay, it bounces off once again, but when we had the graph to be traveling, once we get to x equal to 10, it's going to cross where the graph of the function is going to go from below to above the x-axis. Okay, and I'm not drawing this function according to scale by any stretch of the means, but I just wanted to show you. So we're starting out below, so you got below, then touch, still below, touch, below once again, touch, below once more, and then once we get x equal to 10, the graph is going to cross the x-axis, and the rest of the activity from going past x equals 10, you're going to have the function to remain above the x-axis. Okay, and one might ask, okay, so how did I know that the graph would start out below the x-axis as opposed to above? In other words, how did I know that I started out below and ended up above when it was not, like, say, the other way around? Well, there is an item that's going to be in reference to what is regarded as the end behavior of the graph of a function. And for what we have in the case of end behavior, okay, now we're going to have 4 distinct possibilities to arise. Okay, so you have for a polynomial function f of x is equal to a of n times x to the n plus a of n minus 1 times x to the n minus 1 Again, this is just theoretical notation for some of the polynomials we dealt with specifically. Okay. You have like this could represent like f of x is like 2x to the 4th plus 3x cubed plus x squared minus 7x plus 5. Okay, it could represent something like this. Okay, now for a polynomial function, okay, of this type, okay, now just key things here, okay. You had the highest degree term. It's going to be a of n times x to the n. Okay, so you got your subscript and superscript variable to be the same with the letter n. Okay, and so you got your leading coefficient. It's going to be that a of n. And the degree of the polynomial okay, that is going to be at n. Okay, so that a of n, that's going to be the leading coefficient. Like here, for this expression, your a of n is going to be at 2. And then for the degree of the function, that is going to be the degree of the highest order term. Okay, and just like over here, n would be at 4, while a of n would be at 2. Now, in terms of the n behavior, we have 4 scenarios that can be drawn. Okay, first of all, so just drawing up the categories. Okay. First of all, if the leading coefficient is positive, and we have that n is of odd degree. Okay, so you got a positive leading coefficient and the power of the polynomial function is odd. Now your n behavior is going to be where it is going to be down to the left. And up to the right. Now let's say if we still have the leading coefficient to still be a positive value, and we have that n is going to be even. Okay, now that n behavior, think of it kind of like a quadratic function. If the leading coefficient a is positive, then the graph opens up from the vertex, and we had these parabolas, where upward motion have left half is going up, right half is also going up. So the n behavior here is going to be up to the left and up to the right. And now say if I have the next term, okay, to be where the leading coefficient, or I should say the next expression is where the leading coefficient is negative. And the degree of the function is going to be odd. Okay. Now for what we're going to have in effect is going to be the polar opposite of what we have with the positive coefficient, while the degree is odd. So in this case, instead of down to the left and up to the right, it is now going to be up to the left and down to the right. Then we have for the fourth and remaining case, if we have that the leading coefficient is negative, while the degree is an even value. Okay, kind of like a parabola that opens down, and the leading coefficient is negative, you had to be opening downward, so you have down to the left and down to the right. Okay, so these are your 4 possibilities. All right, now in terms of what we have with end behavior, kind of using this as a guideline. Okay, so if I were to determine the end behavior, and we'll just say that we have the function f of x is equal to 2x cubed plus 1. Okay, so the higher, so for 2x cubed plus 1, so I have only 2 terms. You say the higher or highest degree term is going to be 2x cubed. Okay. All right, so looking at what we have here, so you got the leading coefficient is equal to 2. Okay, so and 2 is a positive value. And for what we have in the case of the degree, when you got the highest degree term defines the degree of the polynomial. Okay, so we have the n is equal to 3. And 3 is an odd number. So looking at the combination, so a of n is positive, and the value of n is odd, so you got positive, odd, and the end behavior is going to be down to the left and up to the right. Yes.
Can you kind of draw out what that looks like?
Yes. Yes, you have down to the left, up to the right. We're looking at the extremes here. Okay. So we've got, I'm going to have one that's going to have specific zeros, but just we're doing a rough sketch. So y-axis, x-axis. Again, this is going to be a rough sketch, okay, but just for the so you have for the end behavior, okay, so you have down to the left, up to the right.
So does that mean on the left side of the graph, on the left side of y, it's going down?
It's going down.
On the right side of y, it goes up.
At the extreme far left, it's going down, and at the extreme far right, it's going up. That is correct.
Okay. All right. Thanks.
Now let's say that we have a function. This is going to be of a somewhat different nature, and I'm not going to draw this according to scale by any stretch of the means, but let's say we have negative 5 x to the fourth. Negative 5x to the fourth plus 2x plus 1. Okay, so we have for this expression, now the highest degree term Okay, and I got these terms in decreasing degree order. That's going to be negative 5x to the fourth. Okay, so your leading coefficient, okay, stemming from negative 5x to the fourth. Okay, so that is going to be negative 5. And the degree of the polynomial, okay, again, is dictated by the degree of the highest order term. Okay, so that is going to be 4. All right. And in the case of what we have for the end behavior, okay, so you got negative leading coefficient, even degree. Again, negative leading coefficient, even degree. In behavior, you're going to have last situation, where you're going to have down to the left and down to the right. And just looking at the dynamics on this one. Again, just doing a rough sketch. Okay. Again, if you were to graph this might look like something kind of different in shape. Yes.
Will we have any problems where the kind of like the n is going to be the same? So like, for example, like 2x4 and then x4 again, or that's not going to happen?
I'll determine. Okay, let me put this up. You might have okay, so you have okay, so like in the same statement you're asking, or
yeah. So
okay, negative 2x to the fourth, x to the fourth. Okay, if you're looking at factored form, like what we did earlier, you could, if you have like in factored form, it could show up. But if you're looking at the expanded form, the degrees are all going to be different. But you might have, in other words, if you have a factor form, like have like negative 5x to the fourth times, let's say x minus 1 raised to the fourth, something like that could crop up.
Okay.
And so you have in the case of the end behavior, okay, so that is down to the left, down to the right. And in fact, just scenario where we could have, you can have zeros that will have the same degree, but I'll give you just kind of a little bit of a layout here. If I have, let's say, yes.
Sorry, can I stop you for 1 second?
Sure.
So when we go back, if you go back to that first graph you did, where you were showing us where it crosses and touches, the one that was like up and down and up and down and up and down.
Mm-hmm.
So for that one, on the left, it was going down. Is that because x?
It's
first
good.
One was -2, because the.
In fact, I'm gonna show you a case here. Yeah, because we're looking at like tying in behavior with the zeros. Yeah, I'm about to get to that.
Okay.
Yeah, so you got like, say if you were to determine the zeros, and also where f of x crosses and touches the x-axis. And third, the end behavior. Let's go ahead and say zeros and multiplicities. Well, you need to determine the multiplicities to find out if it's going to cross or touch the x-axis. But we'll say that we have in the layout. Okay, we'll say that we have f of x. And we'll say we have equal to, let's say we have negative 2x cubed and we'll say have times x plus 4 to the second, and we'll say that we have times we'll say have x minus 5 to the third. Okay. So this is what we have in the case of f of x. So you got a factored form. Okay. Now before I had expanded forms, okay, but now for the highest degree term, what you're going to do, for the highest degree term, what I'm going to do here, okay, I'm not going to square out x plus 4 and cube out x minus 5 and multiply by negative 2x cubed. That would be a very long exercise. What I'm going to do here is I'm going to take, for the factors, including all the coefficients. Now the first factor we have negative 2x cubed, and between x and 4, x is the higher order term, and this is going to be squared. And x minus 5, between x and minus 5, x is the higher order term, and that is going to be cubed. Okay, so just the highest degree term, taking the highest degree elements or portions. So I'm looking at negative 2x cubed. The next I have from x plus 4 squared, I'm taking x, the higher order term, and squaring. And from x minus 5 to the third, again, x is the higher order term, and I am cubing. So I got negative 2x cubed. X to the second is going to be x squared. X to the third is going to be x cubed. And if I multiply everything out, and we have negative 2x cubed times x squared times x cubed, that's the x to the 3 plus 2 plus 3, and that's going to be negative 2x to the 8th. All right, so that's going to be your highest degree term. Okay, and so we got so got a negative leading coefficient and the degree is even. Got negative, even. So the end behavior you have down to the left and down to the right. Okay, so that's going to be the end behavior. Now where the zeros are concerned, and I know we're getting a bit pressed for time, so let me just kind of put this in a little bit of a nutshell here. Okay, so we got with the zeros. Okay, so from x, we got x equal to 0. From x plus 4, I have x equal to -4. And from x minus 5, okay, I have x is equal to 5. Now for the multiplicity, okay, you have 3 for the multiplicity. -4 stems from x plus 4 to the second. 5 stems from the cube of x minus 5. In terms of crossing or touching the x-axis, okay, so you have for x equal to 0, multiplicity is going to be at 3. So it's going to cross at x equal to 0. And we have next, okay, have an even multiplicity that's going to touch at x is equal to -4. And again, 5 has an odd multiplicity at 3, so it's going to cross at x equal to 5. Okay, so this is what we have in the setup. Okay, and just about there. Okay, so we got our zeros. Okay, so you got 0, -4, and 5. So those are our 3 zeros. Now for the end behavior, again, we have down to the left, down to the right. So we got down to the left, down to the right. Okay, and for the activity in between, okay, so at x equal to -4, the graph is going to touch. At x equal to 0 and x equal to 5, it's going to cross. So for the dynamic that will be played out, so reading from left to right, okay, so you have -4, it touches. Once we get to 0, it's going to cross from below to above, and once we get to x is equal to 5, then we have the graph going from above to below the x-axis. Okay, so you have your end behavior down to the left, down to the right, and you got your 3 zeros. At -4, graph touches, but at 0 and 5, you're going to have to end up crossing, and this will be how the behavior of the graph of f of x is going to be carried out.